Today we're going to put a new twist on the idea of conservation of mechanical energy. So we've been talking about conservation of mechanical energy, where the mechanical energy of a system stays exactly the same throughout the entire portion or entire time frame in discussion. So an example of that would be when I take this cart. Now the cart has some wheels on the bottom, which essentially eliminate the idea of friction. So we can say that up here at the top, the cart has a certain amount of total mechanical energy. And because it's on wheels, we can essentially say that during the trip down the table, the cart's total mechanical energy stays the same. So there's conservation of mechanical energy in the trip that this cart has down this incline or down this table. So that looks like this. So over here on the left, I've got N for no friction. So the energy up here at the top, so the energy at the top will equal the energy down here at the bottom. So this car, obviously comes down here and contains a certain amount of mechanical energy at the bottom. And since it's conservation of mechanical energy, and there is no friction, then we can say that the energy at the top is equal to the energy at the bottom. Now that E stands for total mechanical energy. Well, we know that the three types of mechanical energy are kinetic, gravitational potential energy, and elastic potential energy. So we can break each of these two things out into those, right? So the kinetic energy at the top plus the gravitational potential energy at the top plus the elastic potential energy at the top must equal the kinetic energy at the bottom plus the gravitational potential energy at the bottom plus the elastic potential energy at the bottom. But we also know that when the cart, first off, there's no springs any place around. So in reality here, the energy, the elastic potential energy here is really a non-factor. And when we know that the car is stationary up here, we know that there's no kinetic energy at the top. And then we also know that if we take down here to be the baseline, that as the cart approaches that baseline, there's no gravitational potential energy at the baseline. So what we know then is in essence, the gravitational potential energy turns itself into kinetic energy down here at the bottom. So the gravitational potential energy, let me move this over here to realign the equal sign. The gravitational potential energy at the top in this particular situation will equal the kinetic energy at the bottom. And if we wanted to carry that out a little bit further, we could say that mgh at the top will equal 1/2 mv at the bottom squared, and then twice the height at the top times g square rooted will equal the velocity at the bottom. Now, that changes when I take my cart and I turn it upside down. Now this thing slides down the table and things change a little bit. The function of the wheels basically is to take the idea of friction out of play. You can't totally do that, but in essence, you can take the idea of friction out of the way. But as soon as we flip this over, now the wheels are up top, we're sliding this thing along the table. Well, you can clearly see that the car is not going as fast when we slide it on its top as opposed to when we send it down here on its wheels. So how can we account for that in our energy situation? So, if we think about this, I'm going to go in a different color here. Let's go in blue. Well, we still have energy up here at the top, and the car does still make it down here to the bottom. Its wheels are on top. But we can no longer say that the energy at the top is equal to the energy at the bottom. Why can't we? All right, well, let's think about this. In this situation, the energy at the top was equal to the energy at the bottom. Well, that played out in a speed that equaled the square root of 2 times g times the height at the top. But clearly, this speed right here with the wheels is bigger than this speed right here. So while this energy at the top is equal to this energy at the top, because regardless of whether the car is on its wheels or flipped over here, it's still got the same height. So we're starting with the same potential energy right here, but we don't get to this speed. And if we don't get to this speed, we don't get to this kinetic energy. So we cannot say that the energy at the top is equal to the energy at the bottom anymore. Instead, what we must say is that the energy at the top is greater than the energy at the bottom. And why do we have to say that? Well, we have to say that because we know that the speed associated with the bottom is less than the speed over here, which will lead to less kinetic energy than this. So if this quantity here was equal to the kinetic energy when there was no friction, then the same quantity, because again, we're starting with the same amount of energy up at the top, that same quantity here has to be greater than the energy at the bottom that we end up with. Well, if we want to create an equal sign here, we've got to add something to this side. So if I want to say that the energy at the top equals something, well, it's got to equal the energy at the bottom plus some change in energy. Clearly, there was a change in mechanical energy. Now, again, that seems weird, right? Because for so many years, you're saying energy can't be created or destroyed. It just changes form. Yes, if we're talking about all energies, nuclear, solar, wind, thermal energy, if we're talking about all of those, we can't create or destroy that. But if we're talking specifically about mechanical energy, we can have a change in mechanical energy. And that's what this number here is all about, all right? Now, again, this energy can't go away. What's happening here is that friction is doing work. So what have we talked about? Changing mechanical energy requires work to be done. What's doing work on this car as it slides down the incline? Friction is doing work. It's doing negative work because friction acts up the incline while the car moves down the incline. So friction's doing negative work to make a negative change in energy overall to the system. This number here plays itself out as a positive because of where we've placed it in the equation. But this change in energy comes about because friction did work. So the energy at the top is equal to the energy at the bottom plus the work done by friction. Now, that work done by friction and this change in energy, again, is not a change in overall energy. It's just a difference in mechanical energy. We've lost some mechanical energy. But energy, as you know, from middle school, elementary school, can't be created or destroyed. Where does it go? Well, when friction does work on an object, just think about you rubbing your hands together. When friction does work on an object, friction is turning some energy into thermal energy or heat or internal energy. So this delta E right here, right, is energy turned to heat. So that is mechanical energy, ME, turned to heat, or thermal energy or internal energy, all some terms that you might see. Bottom line, we start with the same amount of energy, mechanical energy that is, and we end with less than we started. Where did some of it go? Some of it went to heat. How did it get to heat? Friction did work on the object. So now our math says that the energy at the top is equal to the energy at the bottom plus the work done by friction. Now my blue marker is fading away, so we're going to go back to black. I would have wanted black to be over here and blue to be over here, but that's being said. So look at, we're following now the same steps, except we don't have the energies equaling each other. Now here we have the energy at the top equaling the energy at the bottom plus the work done by friction. But from there on out, basically it's just algebra now. Here's the physics principle. The rest is kind of algebra. Well, what makes up the energy at the top? Well, again, it's the kinetic energy at the top plus the gravitational potential energy at the top plus the elastic potential energy at the top equals the kinetic energy at the bottom plus the gravitational energy at the bottom plus the elastic energy at the bottom plus the work done by friction. This sentence here corresponds to that sentence, except the energies aren't equal anymore. We've got to add this amount of work done by friction over here. But we got the same setup. At the very top, there's no kinetic energy and there's no elastic energy. And at the very bottom, there's no gravitational potential energy and no elastic energy. So this sentence here, just like this one reduced to this sentence reduces to gravitational potential energy at the top equals kinetic energy at the bottom plus the work done by friction. This sentence here corresponds to that sentence. This sentence here corresponds to m times g times height at the top equals 1/2 m velocity at the bottom squared plus the work done by friction. So now we got to take this work done by friction, bring it over here. If we're looking for the speed that this thing is at the bottom, we've got 2 times mgh minus the work done by friction, all divided by m, square rooted, equals VB. Now, it's not totally apples and apples here when we look at this expression compared to this expression. And the reason algebraically is we could cancel the m's over here because every single term had m in it. Over here, we can't do that because the work done by friction doesn't necessarily have m in it algebraically. But you can see here, look at this term right here, 2 times g times h, is really just this term here, 2 times m times g times h, that h being the height at the top. So we have this term. We're just subtracting the work done by friction, which will therefore give us an overall smaller velocity down at the bottom. All makes total perfect sense. Now, the last thing that I want you to be aware of is, hey, don't forget, right? The work done by friction can be calculated, right? So that work done by friction is the friction force times our displacement, F times delta X. So there's a difference. Conservation of energy with no friction, but friction comes in as kind of an external force, changes some of that mechanical energy to internal energy. So we can't say that mechanical energy is conserved anymore when we think about friction. And there's the math to illustrate that.